we'll be focusing specifically on systemic lupus erythematosus, or SLE, and mapping out exactly how these microscopic cells fight, fail, and miscommunicate in this incredibly complex condition. Let's get into it.
Right off the bat, this poses a really terrifying question. How does the high-velocity highway of a perfectly healthy immune system turn into a catastrophic friendly fire scenario? You know, your immune system is this beautifully elaborate network. It's an elite defense force designed to hunt down viruses and bacteria. But in lupus, that highly trained militia just gets confused. It actually begins to recognize self as foreign. But to really understand how that happens, we first need to establish what normal actually looks like.
So let's dive into part 1, the immune highway.
I want you to picture a high-definition animation of your bloodstream. Over on the left, you've got spherical white blood cells gliding smoothly past your healthy tissues. They're constantly patrolling, sure, but they maintain what we call immunological tolerance. Basically, they know not to attack. But then, look at the right side. We see the autoimmune subversion. That beautiful choreography is completely disrupted, and those exact same white blood cells begin to swarm and attack your own healthy native tissues. Now, how do they know who to fight in the first place? Well, immune cells rely on things called antigens. Think of an antigen as a microscopic ID tag sitting on the surface of a cell. When your immune cells come across antigens on germs, boom, they destroy the germ. But in lupus, the ability to read these microscopic ID tags goes entirely awry. The immune system literally starts reading the friendly, endogenous markers on the inside of your own cells as if they were dangerous pathogens. But wait, how does the immune system even see the inside of your cells to make that mistake?
As Dr. Beth Jonas brilliantly points out here, the root of all this cellular chaos actually begins with a massive failure in our body's biological garbage disposal. See, in a healthy body, billions of cells undergo a programmed, totally silent death every single day. We call this apoptosis. It's supposed to be neat and tidy. But in lupus, we see dysregulated apoptosis. The cellular garbage disposal essentially just breaks down.
And here's how that cascade builds up. Normally, macrophages, which are basically the immune system's cleanup crew, eat up those dying cells. But when they fail, those dead cells just linger. Eventually, they undergo something called secondary necrosis. If we were watching that microscopic animation, you'd see these dead cells literally burst open. They flood the surrounding tissue and bloodstream with toxic, hidden nuclear trash, stuff like double-stranded DNA and histones that your immune system was never, ever supposed to see.
And what's wild is that we can actually track this garbage disposal failure down to specific genetic mutations. Take a deficiency in the C1q protein, for instance. That's a crucial tag that tells macrophages to eat dead cells. Without it, you get a near-complete failure to clear debris, which results in a staggering 90% risk of developing lupus. Other mutations, like those in TREX1 or DNase 1L3, mean the body literally lacks the microscopic scissors it needs to chop up and degrade all that exposed DNA. So all this exposed trash leads us to the primary weapon in this friendly fire assault, the antinuclear antibody, or ANA. When that nuclear debris floats past immune cells in the lymph nodes, specialized B cells mistakenly identify it as a deadly virus. In a panic, they start pumping out these Y-shaped autoantibodies. And remember, these aren't your standard antibodies. They are autoantibodies. They specifically hunt down and tag your body's own cell nuclei for destruction, clumping together into dense clusters called immune complexes. But hey, before we assume that having ANAs automatically equals a lupus diagnosis, take a look at this data. Up to 33% of totally healthy people are walking around with a low titer or low concentration of these exact same antibodies. Up to 15% of perfectly healthy individuals have a 1 to 80 titer. Honestly, it is incredibly humbling when you realize just how delicate the balance of our immune system actually is.
So the big takeaway here is that a positive ANA is just a screening test. It's not a definitive diagnosis. Even sky-high numbers can exist in a person without any illness at all. It's simply a marker that some level of self-recognition is happening. For it to actually turn into a destructive disease like lupus, there has to be an amplifier, a spark that ignites the simmering confusion into a full-blown systemic fire.
Which leads us to part 4, the interferon alarm.
1,000. That is the sheer scale of the panic happening inside the body. When those autoantibodies bind to the exposed cellular trash, they form those immune complexes we talked about. These are then swallowed by a specialized responder called a plasmacytoid dendritic cell. Once inside, they trigger an internal alarm system that causes these cells to pump out a massive 1,000 times more type 1 interferon than any other cell in the body.
This massive release creates what we call the interferon signature.
And honestly, it perfectly explains why patients feel so profoundly sick. Their bodies are locked into this exhausting, blaring chemical alarm that simply never turns off. Usually interferon is released to fight off severe viral infections, right? It's what gives you the terrible body aches and fevers when you have the flu. But here, the body is flooded with it constantly. It creates this brutal feed-forward loop. More B cells make more antibodies, which create more immune complexes, which trigger even more interferon.
Eventually, all of this, the uncleaned cellular trash, the autoantibodies, and the raging interferons, it all spills into the organs. The immune complexes physically deposit in the skin, causing that classic photosensitive butterfly rash across the face. They deposit in the joints, leading to painful, boggy swelling. And most dangerously, they deposit in the kidneys, causing active urinary sediment, protein leakage, and a very severe condition called lupus nephritis.
Now, for decades, we blamed B cells and antibodies for basically all of this damage. But modern single-cell RNA sequencing dropped a massive plot twist on us. It turns out, elite killer T cells, known as CD8+ T cells, are directly orchestrating the destruction in the kidneys. These cells are normally designed to act as assassins against virus-infected cells, but here, they actively infiltrate the kidney tissue, mistakenly treating the organ itself as a foreign invader that absolutely must be destroyed.
And this helps explain why lupus is so incredibly hard to treat. As Dr. Joseph Kraft explains, these highly activated killer T cells have a terrifying superpower. They can self-renew, kind of like stem cells. They sit out in the lymph nodes and just endlessly clone themselves. It's like they're acting as an infinite, constant supply line, pumping fresh soldiers directly into the kidney to continue the autoimmune attack, even when standard treatments are being applied.
Throughout this explainer, we've basically mapped out the microscopic battlefield of lupus. We've seen the failure of the biological garbage disposal, heard the deafening interferon alarm, and witnessed the relentless T-cell assault. But it leaves us with one incredibly provocative question. Now that we can visualize this exact cellular choreography and identify the specific immune cells driving the destruction, are we finally on the brink of outsmarting our own immune system and calling off the attack for good?